The final type of solubility product calculation we're going to deal with this week involves trying to dissolve a salt in a solution that already contains the anion that we're trying to get to dissolve. So in other words, the common ion effect is coming back into the picture. So here's an example. Calculate the molar solubility of silver 1 chloride in a 0.5 molar silver 1 iodide solution. So if the common ion effect is part of my equation now, that means that this is not going to dissolve as well because there's already silver in my sample. The KSP for silver 1 chloride is 1.6 times 10 to the negative 10th. Okay, so it looks very similar to a buffer ice table. Right, there's my equation, AgCl, and dissociating in Ag plus and Cl minus. And again, think about it like a buffer, right? I told you in the problem that silver 1 was already in the solution. So that's why this is 0.5. And then, of course, this is 0. So this is 0.5 plus x, and this is just x. So we do our arithmetic, plug in the KSP that we were given, 0.5 plus x, and then x. So we're going to have to do the dreaded quadratic equation. We're going to have to solve negative b plus or minus square root of b squared minus 4ac all over 2a. Solve for x. So there's the quadratic equation. When you solve that, you come up with a value of x of 3.2 times 10 to the negative 10th moles per liter. So that's a really, really small concentration, but think about it. The concentration that's going to dissolve in there is really, really small because there's already silver in there. That's the common ion effect. That's the same principle. That's what a buffer is based on. Right? So essentially you can think of this as like a salt buffer. And that's the end.